Okay, so this is just going to be a overview of the partial f-test. So we use a partial f-test when you want to consider dropping a subset of the predictors. So when I say a subset, it means it could be, one, two, three, or even all the predictors. So we'll let beta 2, so this is a boldface. So this is just going to be like a vector that denotes all the coefficients you want to drop. And let the boldface 1, beta 1 be the coefficients you want to keep. So the null hypothesis is basically saying all the coefficients inside this vector, you want to set it equal to 0, i.e. you want to drop all of them. And the alternative is say at least one of the coefficients is non-zero. So really, if you fail to reject the null, it means you could drop those subset of predictors that are inside beta 2, right? And if you reject, that means you stay with the model with all of the predictors and don't drop that subset. So this is basically saying, can we drop all of the predictors in that subset? So the F statistic is given by this equation over here. The numerator is the key here with the idea. So if you look at the numerator, this is the F statistic from your textbook. This SSR basically represents the increase or the difference in the model fit when you add beta 2, the set of predictors in beta 2. So it's basically saying, right, the idea being if this is large enough, that means it's worth adding these extra set of predictors because they will significantly improve the model fit. Right, so that's why when this is small, this F statistic will become small and then you end up failing to reject and then you drop all of the predictors. Another way to write this numerator, so this is shown in the textbook, another way is actually use the residual sum of squares instead of the regression sum of squares. So we can take this difference as well because the main thing that we realize over here is that SST equals to SSR over plus SSRes, right? So you could basically do some of the math yourself, right? If you put SSR is equal to SST minus SSRes, you realize you get this second portion over here. So it's basically the change in the model fit or the change in the lack of model fit that we are measuring with this partial F statistic. So I'm going to look at a data set with 9 predictors. It basically contains some data on health status of some people in Peru who have been moved from a high altitude to a lower altitude in the urban areas. So let's fit this model and see some of these significance tests, right? And we kind of notice these last 5 of these, right? They're all insignificant. So you think, well, could I drop all 5 of these simultaneously? Now, the t-test, if you recall, only allows us to drop one predictor. Right? When you drop one, all these t-tests will change. So it doesn't mean that you could, if you drop all these one at a time, right, that will work. So if you want to simultaneously drop all of them, you have to carry out the partial f-test. So that's what we want to consider, right? So this is going to be the set of predictors that are stored inside my vector beta 2. And these are the set of predictors that are my beta 1, right, the vector. So, right, the last 5 predictors are not significant, so we want to see if we can discard them altogether. So in other words, we want to test whether the 5th, 6th, 7th, 8th, 9th coefficients are all 0. So these coefficients, all of them are inside my vector beta 2 in the formula. So if the null is not rejected, right, then we don't have evidence that these predictors contribute to the explaining the response. There are actually 2 equivalent approaches to computing the partial f-test. So I'm going to just show them to you right now. So this is the output from R. So what I've stored inside result is the model with 9 predictors, and reduce is the one with just the first 4 predictors, right? And I could use a ANOVA function to produce this table, right? So this table gives me an F statistic 1.22, large p-value, so we fail to reject null, right? And we go with the simpler model. Now, what happens if you want to actually perform these calculations by hand? So let me just push that up. Right, and we know the F statistic, right, SSR of beta 2. So in this case, beta 2 are the last 5, and beta 1, the vector, is the first 4 predictors. R is the number of predictors in beta 2, the number that you're looking to drop. So in this situation, it's actually 5. Mean square residuals, beta 1 comma beta 2. So that's the mean square residuals of the full model. So we know we're using the second way to write it in terms of the sum of squares, the residual sum of squares. This becomes the difference in the residual sum of squares of the smaller model and this bigger model, that chunk divided by 5, right? Because we're looking to drop 5, and we are looking at the mean square residuals of the full model, right? So in this case, beta 1 represents the first 4 coefficients, and beta 2, the vector, represents those that we're looking to drop all the way to beta 9, right? So sum of squares residual of beta 1, the small model, is this 2629. Sum of squares of the full model is 2172, and the mean square residual, right, is basically of the full model, which is 2172 over its degree of freedom, right? So just putting in the bits and pieces, 2629.7, 2172.6 divided by 5 over 2172.6 divided by 29, right? And you work this out, this gives you the about 1.220, which matches up with the computer output. And to get this, if you wanted to work, find a p-value in using R is 1 minus PF, your test statistic, and the degrees of freedom in a for an F distribution, there are actually two, some people call it a numerator and denominator degrees of freedom. So the numerator is 5, right, because we have the 5 over there, and then the denominator is 29. So if you work this out in R, you should get something like this, which is pretty close to what I get over here, right? So that's probably some rounding off over here. So this is one approach, right? And if you had to calculate by hand, this is how some of these values are got, right? So this F statistic consistent with what we got, the p-value consistent with what we got over there. So that's one way to do it. A second way to do it looks a little bit more complicated. It's just to look at the ANOVA of your big model. And the key thing with this approach is to actually be sure to input the predictors that you want to drop last inside your LM function, right? So that's the output we have. So the key thing, so let me just shrink this a little bit, right? So again, we are looking to drop, so just a quick reminder, beta 1 is the first 4, right? And those that we're looking to drop, beta 5 all the way to beta 9. So this is the other approach, where in the previous approach we were looking at a difference in the residual sum of squares, and now we're going to use the difference in the regression sum of squares over here, right? So this is the same formula, but we're going to use the other version to work with this, right? So we know that this is the same as looking at the difference in the regression sum of squares of the big model with all the predictors minus the regression sum of squares of the small model, and that whole chunk is divided by R, which is 5 in this case because we're looking to drop 5, and then we're looking at the mean square residuals of the full model. So now how we get these values, right? It may not be apparent right away where these are. So the regression sum of squares of the full model is basically, you're going to just be adding up all the regression sum of squares associated with all the predictors, and then subtracting the regression sum of squares of beta 1, which is the first 4. So you're going to take the red one minus the one with the small, right, the first 4. Those are the ones you want to keep. So really what you're left with, if you're taking the red minus the blue, right, you're now left with these last 5. So it's basically adding up those 5 over there, right? So it's going to be 1.68, 297.68, 91 plus 10.01, 33.84, right? So that's the whole chunk over here, right? And then that whole chunk we divide it by 5 in the numerator, and then mean squares of the residual 2172.59 over 29. And if you work this out, this also gives you the same F statistic as the previous approach. So really, right, depending on what output you have or what you produce, there are actually a couple of ways to find the partial F statistic, right? So the key thing is always to identify what predictors are the ones you want to keep, which ones are the ones that you want to consider dropping. And in terms of using R, right, you always want to input, right, when you use the LM function, the predictors that you want to drop, you should be putting it last in your set of predictors. So you can kind of see, right, in this situation, right, we do not reject the null, so we can remove these predictors from the model. So this tells us that we can drop all those last 5 simultaneously.